Okay, everybody, I think we'll make a start. As I said, welcome to you all for our EU Green Week event entitled The Role of Geothermal Energy in the Net Zero Transition. My name is Nick Timmins. I am the Principal Investigator of the WISER Lab in Letterkenny University, or Letterkenny Institute of Technology. I am your host for today's event, which is brought to you by the SMARTrenew project, which is funded by the Northern Periphery and Arctic Interreg program. Before we begin, I just have a few housekeeping pointers. Could you please keep all cameras and mics off throughout the session? We are welcoming questions for the speakers. We will try and do one or two questions between speakers, but we will have a Q&A session at the end of the event. And if you have a question, can you please enter it into the Q&A box on your Zoom panel there, and then we will get to it during the Q&A session. If we don't have time to finish all the questions, we will get back to you after this event with answers to the questions, and we'll also be sending each of the attendees the recording of the session after the event. So I'm just going to share my screen here so I hope everybody can see that. So just to give a little bit of background before we kick off, the idea for this event really came from our Finnish partner Sanna Hiltunen of Oulu University of Applied Science, who recognized that three of our partner countries had expertise and experience in various forms of geothermal energy technology. Finland, the Faroes and Iceland. And we thought it would be interesting to share their thoughts in EU Green Week and how these technologies can reduce reliance on fossil fuels, reducing pollution, and really help us to get to a net zero carbon emission. So in these series of presentations, we will look at the experiences, the technologies, and the science of extracting heat and energy from deep underground, or in fact storing it underground, and we'll look at how these forms of renewable energy can help us to this net zero carbon emission state and reduce pollution. So we have 5 speakers for you today. We're going to start with Meinhard Eliasson from the Faroese Energy Department. So we have all of our speakers, bar our Finnish speakers, are actual partners in the SMARTrenew project. Asmu and Anu from the Geological Survey of Finland, we're very grateful for them to contribute as well. They are associates of our Finnish partner in Oulu University of Applied Science. So I'll just move on to our first speaker. Sorry, I just want to talk a little bit about the SMARTrenew project first of all, just to give you a little bit of background. It's a 3-year project funded by Interreg NPA. Has 3 years duration. It's actually going to end now in early 2022. There's a 6-month extension due to COVID. I think that's affected a lot of projects. And our partner countries and organisations are ourselves in Ireland, the WISER Lab, also Donegal County Council in Ireland, Derry City and Strabane District Council from Northern Ireland, Oulu University of Applied Sciences in Finland, Sintef Narvik Research Centre in the Arctic Circle there in Norway, the National Energy Authority of Iceland, and in the Faroe Islands we have the Environment Agency. And this is some of the aims and objectives and a little brief summary of where we are. The idea was to establish a transnational network of countries covering this region, which is the northern colder area of Europe, the Arctic, the northern, the Atlantic and islands, build smart energy rural communities through stakeholder teams in each region. Really, this is an area that is still quite heavily reliant on fossil fuels. It's sparsely populated, it's cold, this project really is to concentrate in this area and bring some innovation in terms of smart renewable energy mix and smart renewable energy storage. The second part of the project was to design and implement pilots, and we have 7 pilots that are well underway, if not completed in the 6 countries. So looking at various types of storage, including water, batteries, and rock. Looking at a renewable mix implementation, including heat energy from the ocean, from the ground, solar, wind. So there's a good variety, and I would encourage you, if you want more information, to go to our contact details, which will be coming up shortly. We are in the 3rd phase of the project. We're coming into finishing the pilots and evaluating the impact of the energy pilots in each region, and looking at the results of how the energy efficiencies and the cost savings will benefit. We will be disseminating these results over the next remainder of this year, and hopefully coming up with some more events really to talk about the pilots and to talk about the project. So we will be in touch when we get to that point. And so there are our contact details. So we have a website, SMARTrenew website page. You can go on there for any details that you want, or information or contact details. And we're also active in various social media as well. So just to get to our first speaker, I'd like to welcome one of our partners from the Faroes, Meinhard Eliasson from the Faroese Energy Department. He's been a senior energy advisor there and has worked in a range of areas related to both renewable energy as well as oil and gas exploration, including assessing the feasibility of ground source heating and renewable power production, as well as projects aimed at improving energy efficiency in the fish harvesting sector. So Meinhard's talk today will explore the incentives, some of the learnings, and the future implementation of geothermal energy in the Faroe Islands. So Meinhard, I'll hand it over to you if you want to share your slides, please. Thanks. Meinhard, you need to put on your mic there.
Okay. Hello. Can you hear me now? Yes. My name is Meinhard Eliasson, and I came from the Energy Division of the Faroese Environmental Agency. And I will tell you a little about how we have done with regard to geothermal in the Faroe Islands, what we have obtained so far, what we have lessons learned, and things like that. If we take the first a little clarifications of what we mean when we say geothermal. In our definitions, we are talking about you can say that when we speak about geothermal, the first people think about is hot steam, geyser, and steam from Iceland. And this is not the case in the Faroe Islands, because we are focusing on the so-called low enthalpy heatings, which is exploited at normal temperature in the shallow subsurface. And that heat is generated from the solar energy, and it is stored in the upper layers and the surface of the ground. And for those of you who don't know anything about the Faroe Islands, I have set up a small map. You can see we are lying here in the middle of the Atlantic Ocean between Iceland, Scotland, and Norway. And we are a total population of 53,000 people. Our GDP is relatively high. It's 20.8 million Danish kroner, and that gives a GDP per capita of 400,000. And we have about 18,000 houses or dwellings in total of the Faroes. The next figure is showing the energy flow of the islands. And as you can see, we are, as many other islands communities, very, very dependent of oil. The first bars are the oil which are used by our fishing and merchant vessels, and it is nearly over 40% of the total energy. And the more light red is oil which is used onshore, and we use it for transport, we use it for industry, and we use it for heatings, and we use it for power production. And at the bottom you can see what we have of so-called renewable energy sources. That is hydropower, wind power, and waste burning. And they are very small compared to what we use of oil. That gives us a big problem because our CO2 emission is very high, and it is growing, and it has been growing all the years since the 1990. So our challenge is to how we can lower these CO2 emissions. And as I said to you earlier, we use a lot of oil for power production and for heatings, and our aim is therefore to reduce the demand and shift over from fossil fuels to renewable fuels. And if you can say, we are to pick up the lowest hanging fruit, and that is that we can look at if it's possible to replace the oil which is used for heating, space heating in houses, and replace it with electricity in combination with heat pumps. And that's what my presentation will be about. And we can say that we 10 years ago started an initiative where we would look at how if it was possible to investigate to find out if rock heating could replace heating with oil burners. On the next slide, you can see a map of the wind potential or the wind resources in the Northern Europe. And you can see that we, on the Faroes, we are in the red area. We have very, very good wind resources. The average wind speed is over 10 meters per second, and that is more than you have offshore in the North Sea, for example. And that's the reason why we think that wind power is a good alternative for us. Another important issue is that if you look at the globe and try to find out what is the mean temperature, you can see that the red area it goes up in the north towards the area west of Scotland and south of Iceland, and that's because of the Gulf Stream. So you can see that we are living in an area where it's relatively warm compared to where we are placed on the northern hemisphere. And this figure is very important, and you need to have it in mind when you are talking about geothermal energy. And you can see that the heat that comes from the sun is at another magnitude than the geothermal flux. It's maybe hundreds or 1,000 times higher per square meter. And here you have a map showing the geothermal heat flux coming from the internal of the Earth. And we are in the area, the light blue area, which means that we have a heat flow about 50, 60 milliwatt per square meter. And that those things I have explained earlier means that we have a ground temperature in the Faroe Islands, which is about maybe from 8 to 12 degrees Celsius, and that is very high compared to what we have in other countries. For example, in Denmark, they have a temperature which is much lower than ours. The next slide, you will see a curve that shows the temperature of the year from on the Faroe Islands, and the thick lines are the maximum or the minimum temperature, and you can see that the maximum temperature which has been measured on Faroe Islands is 26.3 degrees, and the lowest is minus 12.3 degrees. But in the middle, you see the thin lines, the yellow one and the blue one, and that means that the mean temperature is between those two lines. So you can see that in all we have a very stable temperature. It's not very often that we came down to zero. On the other hand, we seldom come up over 10 degrees in the summer times. This figure is a measurements from a scientific drilling which was carried on the island of Suðuroy, which is the most southernmost island, and they managed to drill down to 3,000 meters and hit a temperature of 100 degrees Celsius. And I can also tell you that we have had oil exploration on Faroe Islands from 2000 to 2014, where we drilled 8 wells, and we came down at a depth similar to this one, 4,000 meters, and there we hit the temperature which was about 100 degrees. And to come again to the point what it is all about, we started a project 10 years ago where we tried to find out if the condition for geothermal heating could be applied on the Faroe Islands. And in this case, we hired some expertise from Sweden, and they came up here with equipment, and they carried out a test drilling, and they performed a so-called thermal response test, and made some simulations of what it would like to have a geothermal heat pump on our islands. And the reason for why we contacted Sweden, our people from Sweden, is that Sweden, together with, for example, Switzerland, has been a pioneer in the development and commercializations of this type of heat pump. And they have done it for more than 30 or 40 years. And you can say that the geological conditions in Sweden are in some way similar to ours. The only difference is that they have granite in their underground, where we have basalt. And when they came here, they drilled, I think it was 5 or 6 holes, and they set up equipment to measure the circumstances, the geological data in the hole, and we set up a logging program. And the conclusion was that geothermal heating was a suitable technology for space heating on the Faroe Islands. And to go more detail in the project, we want to find out if, as I said earlier, that if ground source heat pump is a suitable technology, and in this case, you must have in mind that based on the temperature which I told you about earlier, the houses and dwellings in the Faroe Islands, we need heating all the year around. It's not the same as, for example, in Denmark, where you can shut off your heating systems in the summer months from May to August. And the question is, what will these conditions have on the borehole and on the temperature in the borehole? Another important issue was to find out the geological characteristic for basalt. What temperature do we have, and what is the thermal conductivity in the basalt? And how should we dimension a heat pump? And it ended up with some recommendation, and there you can see them. We found out that the geothermal conductivity of basalt is about 1.8 watt per meter per degrees Kelvin, which is slightly lower than, for example, for granite, which we have in Sweden and in the southern part of Europe. But the basalt is very not so it could be very different and not so uniform. So we have a lot of pores and rifts in the basalts, and that means that we have a lot of water in the pore space and the rifts. And they also found out the other parameters. They measured the geothermal heat flux, which I mentioned earlier, and also the borehole resistance. And based on these conditions, they come up with recommendations that if you have a borehole on the Faroes, you can extract energy at 115 kilowatt hours per meter per year, and the momentum amount of energy is 25 watt per meter. And they also find out that drilling a basalt is very easy and it's uncomplicated. And until now, we have managed to drill boreholes down to 400 meters. And if we use that recommendations for a normal family house, which I show you on this calculation, let us say that we have a house 115 square meters, and they use floor heating, and they have well insulated outside walls, roof and ground floor, and we have calculated that the amount of energy is 22,000 kilowatt hours per year, and the maximum effect is 5 kilowatt. That means on a cold winter day when many people take a shower, for example. And if you have a heat pump with a seasonal performance factor of 3.5, then you can calculate that the length of the borehole is 137 meters if you look at the energy requirements, and if you take the effect requirements, it is 143 meters. And then you will be on the safe side. So we add 10 to 15% and ended up with our recommendations of 170 meters. Yes. And what have we obtained since we started this initiative? Until now, we have drilled 843 holes since 2009, and they are drilled all around the islands. You can see the black dots on the map. And we have today we have 2 drilling contractors, 2 drilling companies, and they are operating 3 drilling rigs, and they are active every day. And we have 5 companies who are selling, installing, and servicing ground source heat pumps. And in 2020, last year, they installed 220 new ground source heat pumps. And the government has done other things also. If you invest in a heat pump, you can have the VAT refunded, and you also pay a lower price of power from the power company. And all holes are registered in a public database, which you can find if you go out to the www.korthal.fo. And as I told you earlier, we set up a logging program, and the figure in the bottom of the slides show the temperature in the hole from 2008 until 2020. And you can see that it is very stable. It's the high in the summertime and low in the winter, and it is heated up again the next year. So you can see that the amount of energy which is extracted from the hole is not so high that the hole is cooled down. On this slide, this is our part of the capital of Tórshavn, and this is from the database which I mentioned earlier, and you can see all the holes that are drilled in this area. And to do that, you go into that on the web, and you can click on the so-called green energy, grøn orka. The second last slide is a reminder that it is very important that you build your house with the newest requirements. In 2017, we had our first building construction regulation of the Faroe Islands, where it is stipulated how the minimum thickness of insulation and other requirements to the heating system. And this 3 figures you can see on the left side is the energy amount you use for 3 different buildings, and they are all built according to 3 different building regulations. And you can see that it's very important that you follow the strongest and newest regulations and use thick insulations. So that was all from me. And if you have any questions, you are welcome to contact me. You can find my email address on the last slide here. So that's all.
Thank you very much, Meinhard, and you kept well the time. Listen, we've got one question that's come in here, and I'm just going to ask you it because it's relevant to some of the work that I know you're currently doing. It's from Andy Frew. I know Andy, he works in the housing executive in Northern Ireland. Andy asks, can the geological strata be used for heat storage? For example, can heat produced using spare resources such as wind energy be stored until it is needed?
Yeah, we have been looking at that issue, but I think it could be very complicated because there's a lot of water in the Faroese subsoil underground, and that means that if you put heat up the basalt, it is a risk that the water transferring in the basalt can take the heat away. because of all the pores and the water channels you have in the vessel.
Yeah, it's something you're experimenting with at the moment, isn't it? Yeah.
Yeah.
Yeah. That's great. Thank you very much, Meinhard. I'm just going to share my screen again.
Oh yeah, there we are.
Yeah, sorry, I'm just going to move to the next speaker. So this is Asmundsson from the Geological Survey of Finland. He is an account manager with that group, an enthusiast in geothermal and other low carbon energy solutions, with expertise in engineering, product development and management, and the adoption of shallow and deep geothermal energy in Finland. And so in his talk today, Asmo will explore both of these concepts and their adoption in Finland. So Asmo, I'll hand it over to you if you'd like to share your screen. Thank you.
Yeah, thanks, Nick. Okay, hi to all. I start my presentation right away. Okay.
Yeah.
No. Can you see my notes now or not?
No, that's fine, Asmo. That's fine.
Okay. Okay. So hi to all. I'm Asmundsson. I'm representing Geological Survey of Finland today. So it was very interesting to hear what the situation in Faroe Island is right now, because the geological conditions are quite different here in Finland and also other parts in Scandinavia. So if you watch what's the situation in Finland, the Finnish bedrock is the oldest in Europe, maybe oldest in the world, but that also means it is also the coldest. So you have to drill very deep boreholes compared also to other Scandinavian countries like our neighbor Sweden, for example. But even though the conditions are not the best for geothermal, the use of shallow geothermal especially has grown very rapidly in Finland during the last 2 decades or so. I don't know the latest figures, but I think the Finland is third after Sweden and Germany if you look at the number of ground source heat pump installations annually. So this thermal conductivity, though, is quite high because we do have this granitic bedrock, but the temperature differs a lot between north and south when you look about the soil and bedrock. In the southern parts, the temperatures in the bedrock are fairly good, but in the northern parts of Finland, it could be just above 0 degrees centigrade. And that's a very challenging, it's a challenge for these designers who try to design a proper shallow geothermal system. So we have made this overall map in this picture that shows the potential, but also pinpoints the most challenging areas in Finland. And our capital Helsinki is located in the south here, where the best conditions for shallow geothermal are also found. And about 30% of us Finns live around Helsinki, our capital. So the potential users for geothermal energy are also there. So, and I will use Helsinki as a case example. in my presentation. And because we are geological survey, we have also estimated the potential of the geothermal energy also. And the temperature levels are not so high compared to Iceland, for example, or Faroe Islands before, but we do like to drill deep. So these 1.1 to 3 kilometer deep boreholes, or medium deep boreholes, like we like to call them, they have raised some interest. Especially these energy companies are very interested to drill 1 to 3 kilometer deep boreholes nowadays. So because you don't need a massive rig for that, and the drilling costs are smaller compared to actual deep drilling. But my colleague Annu will show you a case example later about this medium deep geothermal. Of course, Finnish government has some goals about carbon emissions, and we Finns we have decided to be carbon neutral by 2035. And Finnish government has also decided to quit using coal by 2029. And currently, more than half of Helsinki's district heating is produced with burning coal. But coal has already, of course, been replaced by biomass in many cases, but burning in general, it is not a sustainable solution for the future. And Helsinki also has been seeking alternatives for burning. And geothermal energy could at least be one of them, one of the solutions. And so they have set a target in the future to raise the geothermal share up to 15%. That's a target, but at least they have set it. So I already showed you the overall map of Finland, but we have been also estimating the geothermal potential for cities like Helsinki, you see here. In one large study, the whole city area was divided into 1 hectare squares with 25 boreholes inside them. The heat demand of Helsinki is about 6.6 terawatt hours annually, and we have estimated that the shallow geothermal is so large that in theory, at least, it could cover the heating needs of the whole Helsinki for decades to come. But of course, that would require the whole land area of Helsinki to be drilled full of boreholes. And in this right side picture, you can see an example of Borehole Matrix on the city map. The boreholes are 300 meters deep. And like we all know, there in urban areas, there are always limitations for drilling. There are underground spaces, tunnels, cables, etc., piping. But however, nowadays it is possible to drill even 1 kilometer deep boreholes using normal drilling equipment, and therefore partly avoid those limitations. So fewer but deeper boreholes can still provide enough energy for heating purposes. And based on our report we did for Helsinki, the Helsinki City Planning Division made this online map, Energy and Climate Atlas for Helsinki. So in this atlas, you can compare heating energy needs for buildings and also see the energy estimations concerning shallow boreholes. And shallow means up to 1 kilometer deep boreholes. And this atlas is one tool for decision making, whether you're renovating energy system or planning a whole new building, for example. But of course, it's not a precise designing tool, but at least it gives you a rough estimate of shallow geothermal potential. So you can pick a plot and see what's the potential right there. And like I mentioned, we like to drill deep. There's one ongoing deep geothermal project in Finland near Helsinki. This ST1 is an energy company who mainly focus on oil products, but they have been finding new ways also. This project started back in 2014, and with these 2 deep wells extending up to 6.5 kilometers, it's the world's deepest industrial geothermal energy project right now. The project is a pilot, and they aim to explore the technical and also economic feasibility of deep geothermal in Finnish conditions especially. And this project is partly funded by Ministry of Economic and Affairs and Employment. They did get a 10 million start money for this project, 10 million euros. The challenge in this project is how the heat can be extracted from the rock. And this EGS, it is done by circulating water as a heat transfer fluid in the formation between these 2 deep boreholes. And this natural level of hydraulic conductivity is very low and provided only by natural fractures of the rock. And in most cases, the natural hydraulic conductivity is too low for EGS production, and it must be improved by hydraulic stimulation. And in this stimulation phase, large amounts of fluid are injected into rock. That water widens the natural fractures and enhances the conductivity. So you are making one kind of heat transformer into the bedrock. And this project has a network of geophones around this drilling site, and they were monitoring seismic activity during drilling and also during this stimulation phase. And some microseismic activity it was expected, of course, and also measured. This 1.67 in magnitudes. And it caused some noise and mild vibration on the ground. This deep heat project has had some delays, but hopefully it will start operating later this year. My last slide is here. Even this deep heat project is still under construction. Our survey has been asked to do some deep geothermal exploration also in Helsinki area. And we carried out studies near city center last year with this district heating operator, Helen Limited. And we used this reflection seismology method for this study. So now the most promising locations for utilizing deep geothermal energy, they have been mapped. And this energy company, Helen, will start test drilling on one site later this year. And this drilling project is also partly funded by our Ministry of Economics. And I personally hope that part of this upcoming EU recovery funding would be used also for other geothermal pilots in other Finnish countries, but let's see what happens. So thank you all, and here's my contact info. If you have any questions or like to share your information, please feel free to contact me. Thank you.
Thank you very much, Asmo. That was very interesting. These big super deep holes. I see you've had a challenge there in the Q&A. Marek from Poland says, enjoy it because this year we're going drilling 7,000 meters geothermal in Poland. So
they will break our record, yeah.
I just have one quick question, Asmo. Looking at the graph of or the map of Helsinki with all those boreholes, obviously, you mentioned some of the practicalities of drilling underground in the city, but structurally, with so many wells, how would that affect it? Is it feasibly possible to drill so many boreholes in such a confined space at such a high sort of resolution?
Okay, we do have some big borehole fields. There can be up to 300 boreholes in one area. Yeah. About space between 15 to 20 meters between them. So it's possible, yeah.
Yes. Okay, that's great.
But you have to design the whole system so it works correctly, and there should be enough heat in the bedrock also.
Okay, that's great. Thank you very much, Asmo. I'm just going to share my screen again. We're going to move on to the next speaker. Give me a second. So this is Asmo's colleague, Anu Martinkopi from the Geological Survey of Finland as well. Anu is a geophysicist, and her main experience is related to geothermal energy research and development projects, the design of large, shallow geothermal energy systems, thermal response tests, and geothermal energy potential mapping. Anu is developing novel solutions for geothermal energy utilization in Finland as a part of GTK's Geothermal Energy Group. And she will present an assessment of geothermal energy utilization opportunities in the area of Muhos Formation, which I'll be interested to hear what that really means. So thank you, Anu, if you'd like to share your slides.
Thank you, Nick. I try to find my screen here and share. I put it in presentation mode. So is it okay? Can you see my presentation?
Yeah. That's perfect. Yeah.
Okay. Hello everyone. My name is Anu Martinkopi, and I come from the Geological Survey of Finland. And I would like to introduce you our project, which ended recently, and tell you about the assessment of geothermal energy utilization opportunities in the area of Muhos Formation. And as you already may know, Finland is not a so good candidate for geothermal energy utilization compared to high enthalpy areas. as we have a thick and cool lithosphere, and thus geothermal heat flux density and geothermal gradient are typically low. And also our crystalline bedrock has naturally low permeability, low porosity, and water content. But instead, the thermal conductivity of Finnish crystalline bedrock is relatively high, with some exceptions, like here the Muhos formation, which is a large sedimentary claystone deposit in northern Ostrobothnia. And the width of this formation is about 25 kilometers and the length of 80 kilometers. And the thickness is as much as 1 kilometer in certain areas. And below this claystone deposit exists a granitic basement or bedrock. And in addition, the Muhos formation is covered with loose sediments like clays, silts, and sands. So their thickness can vary from 20 meters up to 120 meters. It's quite huge thicknesses of overburden. So this claystone and overlying soil deposits together form like an insulation for heat flow from the deeper parts toward the ground. And as this claystone has low thermal conductivity, it produces the higher geothermal gradient, and therefore the temperature beneath the claystone formation at the interface of granite is higher than it would be otherwise be in the corresponding depths. So in the Finnish scale, it is actually the temperature level what makes this Muhos formation an attractive target for medium deep geothermal energy. And the red line in the picture here, I have a different screen. It shows the measured temperature as a function of depth from almost 1 kilometer deep drill core, which is located in Limminkä at the Muhos formation, and the drill core is completely covered with claystone. And the average measured thermal conductivity is 1.86 watts per meter Kelvin, and the geothermal gradient is as much as 2.6 Celsius degrees per 100 meter, which is high in Finnish circumstances. Okay, then you see other black lines here, and the reason to present them is that we wanted to model the temperature change in different geological scenarios, varying soil and claystone thicknesses to evaluate the temperature up to 2 kilometers, as we currently don't have any measured data from those depths. And related to a single 2 kilometer deep borehole, in the best geological scenario, we have 100 meter thick soil layer combined with 1 kilometer thick claystone deposit. And in the weakest scenario, we have only 20 meters thick soil layer and 100 meter thick claystone deposit. So as you can see, the temperature difference here at the bottom of 200 meter deep is over 10 Celsius degrees, which have naturally an effect on the thermal energy yield from the medium deep boreholes. And the black line in the middle represents a situation in Kirkkosaari, in which the municipality of Muhos is interested in utilizing geothermal energy, as there is no existing district heating network. The main focus of the project was to evaluate the thermal energy yield from a single 1 and 2 kilometer deep borehole and take account the geological circumstances and compare the results with conventional systems by estimating how many shallow 300 meters deep boreholes would be replaced by one medium deep borehole. And a few words about the numerical modeling. We used COMSOL multiphysics to simulate the conductive heat transfer over 25 years into the future. And the heat extraction was assumed to be constant throughout the year, throughout the 25 year, to get annually the maximal amount of energy from the ground using a coaxial PHE. And we assumed not to drop the borehole wall temperature below 0 Celsius degrees. And also we used the maximum volumetric flow rate with acceptable pressure losses. And we modeled the open loop coaxial PHEs as two-dimensional axisymmetric model. And we used water as a working fluid. And the water injection was assumed to be through annulus here, and the heat extraction through this vacuum insulated pipe. And here are the physical properties what we used in the modeling. So as a result number 1, I want to point you out the constant thermal power from 2 kilometer deep borehole, which is represented in the picture of the right side. The thermal power is presented as a function of soil thickness. It varies from 20 meters up to 120 meters. And we used the highest possible volumetric flow rate of 6 liters per second. And the results are presented at 2 scenarios where the soil layer is either sand or clay, which have different thermal conductivities and which are combined with clay stone thicknesses of 100 meter or 1 kilometer. In the weakest scenario, the claystone thickness was 100 meter, and in the best scenario 1 kilometer. And with the flow rate of 6 liters per second, it is possible to achieve the constant thermal power of 120 kilowatts in maximum, which means in thermal energy annually about 1 gigawatt hour. And as a result number 2, you can see here the inverse relationship of thermal power and the outlet temperature of working fluid as a function of flow rate. Here is the power, flow rate, and here is the outlet temperature. And please note these results are presented from the last simulation year, which is 25th year. And as you can see, at low flow rates, we can achieve a higher outlet temperature of working fluid, but lower thermal power. And as the volumetric flow rate increases, we can get more thermal power, but the outlet temperature drops. So either the thermal energy production or the outlet temperature of working fluid can be maximized, or an alternative, they can be simultaneously optimized so that the reasonable temperature for temperatures for heat pumps as well as heat production rates are expected. As a short summary, from a single 2 kilometer deep borehole, it is possible to get annually approximately 1 gigawatt-hour of thermal energy as the maximum flow rate of 6 liters per second and constant heat uptake are considered. And from a single 1 kilometer deep borehole, it is possible to get 300 megawatt-hours annually, respectively. And in the geological setting of Kirkkosaari, a single 1 kilometer deep borehole could replace 9 to 15 shallow 300 meter deep boreholes to cover the same amount of energy. And a single 2 kilometer deep borehole would replace 25 to 40 shallow boreholes. So the conclusion is that in the Finnish scale, the advantage sought from medium deep boreholes may be related to maximize the heat production with high flow rates and lower ground area requirements compared with conventional PIG fields, or with lower flow rates, a higher operating fluid temperature, which allows heat production coupled to a heat pump system with good efficiency and thus heat distribution at higher temperature levels. Thank you for listening, and if you have any further questions or want to contact me, here my contact information, so please don't hesitate to email. Thank you so much.
Thank you very much, Anu. Very, very interesting presentation. It certainly is important to know the geological structure underground to maximize performance. Please, if you have any questions, to forward them into the Q&A. We're going to actually move straight ahead now because we're slipping behind a little bit. So without further ado, I'll bring up the next speaker, please. I'm just going to share my slides here again. So our next speaker is one of our partners again from Iceland. This is Ragnar Asmundsson from the Energy Fund in Iceland. Ragnar is a PhD in physics and has worked in the energy sector in Iceland and in New Zealand, coordinating European and national energy projects, including the HiTI high temperature geothermal tool development effort and the implementation of industrial-sized seawater heat pumps for the island of Vestmannaeyjar. I hope I pronounced that right. Probably haven't. Ragnar will talk about and explore the adoption of geothermal energy in Iceland, including incentives and recent explorations into deep supercritical geothermal systems. So Ragnar, if you could share your screen. Thank you.
Yep. Thank you, Nick, and hello, everyone, everybody. I will try to very briefly cover how geothermal was applied in Iceland to make a certain transition from using oil for heating. And then I will go briefly into the future on how geothermal could potentially be applied for future energy transitions ahead of us, mostly in transport. I'm at the Energy Fund in Iceland. That's this logo here on the right, and on the left you see the logo of the Energy Authority of Iceland, Orkustofnun, where the fund is where the fund resides. Iceland is known for geothermal. That's because we have many volcanoes. There is actually an eruption ongoing at the moment in the Reykjanes area. It's now a tourist site, so you can, if you're tired of COVID, you can visit Iceland and walk to the site. It's not far from the international airport, and people are already there with their bikes and rucksacks, Okay, why is that? Why do we have geothermal in Iceland? That's because we are basically on two tectonic plates, and they are being separated, and we have constantly earthquakes ongoing, and you can sort of see the shape of the, maybe you can draw sort of a line or a horseshoe-shaped form across Iceland, where the split occurs between the North American and the European plates. Right now we have this sort of more activity of earthquakes near the eruption on the southwestern corner, but these are small earthquakes. You see on this graph here that there are no earthquakes beyond 3 in magnitude, so we barely notice them normally. And for this reason, we also then have high temperature geothermal areas, and that's the gray area in the center between the tectonic plates where the Iceland is separating. And we therefore have high temperature that we can produce directly from the steam generated from underground and produce electricity. But of course, we have a lot of waste heat from that process, and it's used in the main urban areas. Outside those areas, where you see the red and going into sort of orange and then finally yellow, we have, let's say, medium temperature geothermal areas, which have been harnessed for the urban areas, mostly outside the high temperature zones. But we still have regions on the outskirts of Iceland, on the far east, and then far northwest, and then of course on the islands, small islands outside of Iceland, where we are not harnessing geothermal, and that's where we are trying to use sort of more standard technology and smart technology. That's why we're in the SMARTrenew project. You could say, probably could argue that Iceland became renewable on land by accident. We were a very poor country from the 1300s to 1800s. That's where we had a really bad spell of weather for 500 years. So we sort of had to use turf houses and other things available, burnt all the forests for heating. But that's all, nowadays that's all considered to be renewable activity anyway. And then we had to turn in more modern times to geothermal for heating of more cemented houses, let's say. And here is a picture I'm going to dwell on for a half a minute at least. It shows an energy transition, and the black region is oil and coal, which was used in the 1950s. And we then had maybe a 30% share of geothermal used in the most urban areas, mostly in the southwestern part. But there was let's say, a political decision taken sometime in the 60s, and that's where the white line sort of starts to rise here on the graph. A political decision was made to fund a transition from oil and coal into geothermal, and that's where the white line indicates the money going into geothermal projects outside the main areas. And you see then how the oil and coal use drops as the funding is increased, and this is integrated amount of money. So at the end of this story, there's a flat line where the sort of end of a transition, and we have no black areas anymore. So we are only using geothermal or electric heating. That's the blue part, electric heating. Okay, so we are done with that. So with the transition on land for space heating, that's finished. So it's all renewable and from geothermal or electricity. But we are now facing another transition on the transport, both on land and ocean, and of course in the air. And that's a more complicated story technically ahead of us. And we are thinking how we can use geothermal in that story as well. We probably need to drill much deeper into the volcanic regions to get even higher temperatures to allow processes where we can manufacture electrofuels using energy from, let's say, much hotter regions. And then we go into supercritical water. If you drill deeper, you go into the fourth phase of water, and allowing you much more flexibility in production of future renewable fuels. And the way to do that, that's let's say we use relatively known technology. This is a picture from roughly 2000, when these investigations started. We use standard wells down to 3,500 meters roughly, and then drill down to maybe 5,000 meters or so to get into the supercritical region. And and we already have 2 or 3 wells drilled in this concept, depending on how you count them. But here is one of them, a photo I took in 2010 when we were visiting one of the wells there in Krabla area. And it doesn't look like much here, but if you look closely in the center of the image, there is sort of a blurry background. And that's because we are looking through superheated steam. So it's dry steam, basically. But then the water starts to condense above here. So this is not a cloudy sky. This is actually just steam starting to condense simply because it's now colder up here. Normally, in a normal well, you get steam immediately from the well. This is a pipeline sort of coming from the well itself. This is just a gravel mount on top of a silencer. It's not a volcano. Okay, we are already using geothermal for various other purposes other than power production and heating. The far right part of let's say close to center right area of this image shows a power plant. But to the left we have sort of a waste heat from the power plant. And this is actually the so-called Blue Lagoon, which is one of the best known tourist attractions in Iceland, and it's now a tourist place, therefore. But to the far right and bottom, you see a small factory which has been producing methanol, which is one of the electrofuels. And they're producing using the renewable electricity and the CO2 coming from the boreholes, combining with the water, which is then split into hydrogen and oxygen to make methanol. So this is already, the story has already begun towards making electrofuel using geothermal. But we need more, let's say, varieties and maybe less expensive processes. We could produce something else like ammonia, which is not coal-based. And here we see a ongoing project that we are involved in, where we are using ammonia in the 2 tanks on the left, and it's connected to a cracker that splits it into hydrogen. And inside this container on the right, owned by GenCell, which is the technology provider, there's a fuel cell, hydrogen fuel cell, which generates then roughly 4 kilowatts for a communication company in Iceland. So Okay, that's already started. I just want to, at the end of this short presentation, to tell you about a project, which is a European project, which is ongoing, called Geothermica. And it's running right now, and it's a platform to share knowledge and know-how in geothermal across at least the European region. And there are many nations, like Ireland, for example, is in there. And right now there's a call being opened on accelerating the heating and cooling transition, they call it. Okay, thank you. And here are my contact details.
Thank you, Ragnar. That's very interesting. I'm going to just keep your questions coming into the Q&A. I am going to move on to our final speaker. I'll just share my screen again. And this is a colleague of Ragnar's in Iceland. So Sigurður Friedleifsson is the CEO of the Energy Agency in Iceland, has an MA degree in environmental science, has worked in the energy sector for 15 years and been the manager of the Energy Agency since 2005, working on improving energy efficiency, energy transition in transport. I think he was the first guy to drive an EV in Iceland, is that right, Siggy? Implementation of new energy techniques and raising awareness of good energy practices. And he will explore the benefits of community intervention of geothermal adoption in Northeast Iceland. So he's also a partner in SMARTrenew. So if you could share your slides, Siggy, and you can start. Thank you.
Okay. Do you see it?
Yeah, you just want to hit your, yeah, that's fine there, yeah.
Okay, everything is okay. You can hear me and everything. Yes, I'm going to talk to you a little bit about how we in Iceland have been using geothermal energy and take our area where our office is and our workplace, me and Ragnar, so it's the northeast part of Iceland. As an example, of course, like Ragnar said, we use geothermal energy almost everywhere in the country. But some areas that we call cold areas, it's the far east part and the far west part, we use electricity as the main heating. Yeah, as you know, and compared to Finland, that I learned now just recently, it's the oldest part of Europe. So I guess we can claim that we are the youngest part of Europe. Iceland is renewing itself every now and then. That's nice, makes good scenery, and you can visit every other year and you get a new country to visit. So, but the main blessing of this very active geothermal energy we have in Iceland is, of course, how we utilize it. And I will give you kind of example of that from our part in the Northeast. As you know, we need, from the consumer side, we need 3 sectors to fulfill when we produce and use energy. And sadly, of course, this was the case for Iceland, as you saw in the graph that Ragnar showed you. And this is still the main thing in the world, where we use fossil fuel to meet the demand from all these sectors, where we take unsustainable carbon from the ground
and burn it for electricity, for heating, and for transport, and throw it up in the air where it's getting problematic. Here in Iceland, we decided to do it differently and are trying to change this picture totally. We have started, of course. We simply plug into a volcano and produce electricity and, of course, heat. So that's fixed, and we can also now, with the technique that is ongoing, drive our cars on geothermal energy. So this is the future we are heading to, quite fast, but maybe not fast enough. But this is the final scene we want to see, where we cut the links between the carbon in the ground and the carbon in the atmosphere, and keep it where it is. This is the area I was talking about, northeast part of Iceland. And bear in mind that we are only talking about 30,000 people living in this area, with the main town Akureyri, where our office is, with 20,000 people. And they are distributed around the area in many small towns. This is not as great geothermal area as the capital area. So actually, the history of geothermal utilization in these areas has been a little bit more difficult, but still successful. And that is maybe one of the story we want to tell outside our country, is that even though we are blessed with this nice, cheap, green energy source, it has actually been or was extremely difficult to harness it in the beginning, both expensive and technically difficult at that time. So it's not like there are just volcanoes in every town. We need to find the spots where the heat has kind of went from the main volcanic areas in the highlands with cracks after earthquakes. And then maybe the main problem is to find the best spots where we have heat and we have water. So these two elements have to go together to find the good spots to harness. But after we harness it, with all the difficulties that we have, for example, for the biggest town, the main action was around 1975 to 80, with extreme difficulty of drilling and trying to find the hot water. Many holes didn't work, etc. And it was a huge investment and a risk that was taken. But after that, it's all hidden. It all goes all in the ground. The people forget it, and they just simple now. It just comes into the radiators and no problems. And that is also a little bit risky, that people forget how extreme resource this is, because this is what it used to be. And now it's just underground, clean, and no problem, and that gives us a little bit risk. People forget the heroic activity that people and the bold decision people made in the early days. Because I'm telling this because this is actually what we need for further improvements on a global level in the transition to clean energy. And just to give you extreme numbers that people don't realize anymore, that this is not a gas pipe. This is a geothermal pipe right by my house. Usually it's underground. It's one of the few one in the country that is above ground. That's why it's very nice to show especially foreigners, this pipeline that people of course assume is gas or oil, but this is just clean hot water coming directly from the underground. And as you can see, the savings in house heatings are humongous. And these are numbers that you have to compare with the population of 30,000 people in the area. And the savings are so much that you don't have to have a PhD degree in economics to see that without this, everything would be totally different in Iceland, because I mean, most of our income would go into this area of just keeping us warm. Or on the other hand, we would never build up this society as we did without this resource. So this is, I mean, looks like a easy money and a gold digging venture, but the thing is that when you look back, and that's maybe the lessons we have to look at and learn, that when you try to fit this business model of drilling and putting up a district heating in this area, it just doesn't fit in a normal business Excel sheet. But still, we are here, and nobody wants to go back. So there is a kind of a gap between like a normal investment thinking business models and reality, because this is has been a lottery for us, but and maybe it was a good thing that people didn't have Excel at that time, because I guess the investors would say no with the outcome of the Excel sheet, but somehow we are here, and nobody wants to go back. And we are in good place, like Ragnar said. You can see here the average district heating price in Europe. We see we are of course on the bottom, and that's very good, especially because here you can see how much we need. So you can think of because we need the most. We are even far more north than Faroe Islands, so if they have to heat the house the whole year, we have to do almost more. But then with these two slides, you can see how lucky we are that we can take down the district heating price without subsidies down to that. But here's maybe the main slide, and that is the in simplest form as I can put it up, to see how people, the mindset of people in the 80s when they were putting up the district heating in the area. So this was the price in Icelandic kroner that they were paying for the cubic meter of hot water. And because they accepted that as a very future investment, that maybe was kind of on par with oil, you could say, in the beginning, because that's how these projects work. They have huge initial cost, but then in time it goes, of course, down, and the price have a potential to go down, down, down. So in the beginning, they had the courage to, even though we have to bear in mind that they paid this price, maybe it was a pair of oil, but a little bit cheaper, but they also have to change and make investment in their houses, many of them. So you can see how much they did for like future generations, that now just have it, don't have to do anything, don't have to put any investment in, and get 1/3 of the price per cubic meter than people in the beginning had. I am afraid that we don't have this mindset anymore. But for like social project like district heating, and I'm not only talking about district heating projects in Iceland with geothermal energy, I'm talking about district heating projects everywhere in Europe where we have some kind of mixed source of renewable heating. This mindset has to come in if we want to make it reality. But usually district heating make a good future prices for the consumer. As you know, we have a little bit extra, of course, now, and we can use it a little bit wildly. This is all outdoor pools in many of the small towns. Remember, we're only 30,000 people. This is my pool. Bear in mind, there are only 200 people living in that village. And we have it open all year around. So we're a little bit spoiled with the energy source, I know that, but still, I hope you remember the courage we had in starting this. That was a real thing, even though we are cashing in now quite heavily. A little bit more about, because we are also lucky in the area that we have also steam powered. I was talking about what we call low heat. That's the heat we use directly for district heating. But in some areas, we have high temperature vapor possibilities to produce electricity with the geothermal heat. And we are lucky in the area that we have such potentials, and we already have three power plants that produce electricity. Just to show you how much it is, that this is the amount of electricity that we produce in the area. This is a big number. To put it in perspective, this can drive everything in 900,000 homes with electric car. And again, I remind you that we are only 30,000, so we have a little bit extra if you want to move here. So actually, that goes for the country, that just the energy from the geothermal power in Iceland, both electricity production and heating, can fully be covered with transport for the whole country. And maybe if you know the power sector in Iceland, you will be a little bit shocked, because still 75% of the energy produced in Iceland is hydropower. But if you take out the big users, the heavy industry, we could drive the whole society without some aluminium factors, only with geothermal energy. Transport, heating, and electricity. So that's just to put in perspective how huge resource this is. Just to have a little bit connection between all the places, because I'm familiar with that you don't have the same amount of active volcanoes as we have. But there's a similarity between these projects. Usually also geothermal projects that we are very interested actually in your presentations about drill holes in, you could say, colder areas, is also relevant for us for the last electric heating users. And this has the same story, with a big initial cost and then huge savings in the long term. Okay, I think I will just stop here. That's my contact info if you have some questions or want to contact. Thank you.
That's great, Siggy. Thank you very much. I have, I'm just looking at the time now, it's 20 to 12, we've run over a little bit, but we have some time for question and answers. Just one question for Siggy, seeing as that's the last presentation today. Just have you exploited all the volcanic hot water And do you see growth in geothermal drilling for ground heat in cold areas? I think you sort of alluded to that at the end.
Yes, it's a good question. Actually, me and Ragnar is working on a paper now, or document about, you could say, the last Mohengens in the Iceland not using geothermal energy. And I think with some enlargement of district heating areas already in place, maybe 1 or 2 new district heating places, and then I think we are in end of our era of direct use of geothermal energy, and have to like sweep up the last 5% with heat pump solutions that we similar that we have been talking in the early stage here. For the power plant, like electricity production, yes, we have a lot of potentials, but many of them are in sensitive areas in the highlands, so it will always be debatable if we want to harness them or not regarding nature reserves issues.
That's great, thanks, Siggy. Just going to the questions in the Q&A here. I've got a question here from Juanita Blue. How you doing, Juanita? First of all, to Ragnar. Great presentation, particularly the slide that demonstrates that the more funding that has been put into use of renewable energy, the less coal, etc., has been used. Do you think this is a key aspect that needs to be addressed in Europe? Obviously, Iceland is lucky in that you can rely on geothermal. Do you think putting more funding into development of renewable energy will make a difference in nations that do not have the same type of resources? Ragnar, if you could take that one.
Yes, of course, money will usually move something. So I think, of course, when people realize that it can be done in this way, you can get actually rid of all the oil that you are using and all the coal you are using for heating. That's in all of Europe and actually in everywhere on Earth. Yeah. You can apply this technique, and it's of course slightly more complicated if you don't have geothermal on surface like we do, but it can still be done. It's just a mixture of technologies. You may need to generate electricity as well for a heat pump, or you have to have a sort of more complicated heat exchanging system where you are resided, but you can use geothermal everywhere, yes.
Maybe I should add to that for the Energy Fund in Iceland, maybe the best part was the how they helped to share the risk, because these projects were sometimes very big compared to the municipalities that were going for these big projects, and they got these loans from the Energy Fund, and if everything went down south in the project, the Energy Fund like took the risk with them. So that was a big thing to help people go for it. So I think just that idea of having a national fund helping with the risk management was a big thing, and help to make the municipalities more courage to go for it.
Yeah, I think that was interesting to learn that, because I think people assume that it was always easy for you, you know, and that it wasn't a big step, that it was such a big step in the beginning to come up with this investment, to take this chance. Just I have a question here for Meinhard. Just in the Faroes, with such a reliable source of wind, world famous for its high levels of wind energy, how do you see this geothermal development compete economically with wind, or is there a balance there to be had between these two sets of renewables?
Yeah. I don't mention in my presentation how much wind we have today, but we have, I think we have 4 wind parks, and they have a capacity of approximately 25 megawatt. And the plan is that within the next 12 months, we will set up 2 new wind parks, and the capacity will be nearly tripled. It will go from 25 megawatt up to maybe 50 or 60 megawatt in total. And the biggest problem with the wind is the storage, because if you have so much wind on your system, you need some form of storage. It could be pumped hydro or batteries, and of course it is obvious that it is very convenient to shift over from oil-fired burners to use electric heat pumps instead. So that is, I think that these 2 things they are linked together. If you set up wind, you need something to use the wind for, and that is heat pumps, and of course electric vehicles. So they could be charged when the wind is blowing.
You mentioned when we were talking about boreholes there for heat pumps. Just like, would it be 1 borehole per house, or would you have 1 borehole for several houses, or how does that work?
Yeah, as it is today, it is very normal that we have 1 borehole per house, because it's very easy to bore. It takes only 1 or 2 days to drill a hole of 200 meters length. And the cost of the hole is approximately maybe 50,000 Danish kroner, which is about 6,000 euro. So that's very cheap compared to what it costs in other countries.
I have one question, Maynard, because it looks like that you have a huge potential with electric cars as a energy to store energy, because I mean, we have now electric cars with 300 to 600 kilometer range. That I know, because I've been in Faroe Islands, that you don't need. So you have compared to other countries, maybe more potential to have this as an energy storage.
Yes, that you were quite right. Yes, that's so. Yeah, we have a lot of cars in Faroe Islands. I think we are a population of 53,000 people. And I think that we have 27,000 private cars, so that's less than 2 people per car. And until now, I think we have registered about 400 electric vehicles. So.
Yeah, you don't have to be ashamed of that number. So we have more cars in Iceland than car licenses.
Yeah. Yeah.
This is a question. This is a general question. I'm going to open up to all the panelists, from Jessica Gecko. To all the panelists, what incentives are key to adopting geothermal in other regions that we can learn from? So suppose, for the general incentives for regions in the world that haven't or are not exploring geothermal, what are I suppose the main top incentives for exploring this? Big question. Anybody can make a start.
Yeah. I think in the future we will see that heat pumps will be more cheaper to buy, because in reality a heat pump is a very simple equipment. And if you take today a ground source heat pump, maybe it cost about 50,000 Danish kroner, and you can buy a freezer or a fridge for less than 1,000 kroner, and the heart of both are the same. It's a compressor. So I think that in the future heat pump will be cheaper than today. Yes, and it will also be cheaper to drill a hole. So that will result in that we will see more heat pumps.
Anybody else like to comment on it? I suppose we need to know, one thing I've learned from the Finnish speakers today, you really need to know what's going on underground to maximize your geothermal potential. So I suppose surveys are required before you do any of this sort of work.
Of course, you have to know the geological conditions. Where are you going to drill? And you need the drillers also. So it's some kind of hard start. Somebody has to start the drilling. So there's always need for pilot scale experiments first in every place where you are starting to use geothermal. But it's quite easy to find the geological conditions. There are surveys, there are other institutions that do know the geological data of the area.
Thank you. I'm sorry, I'm just, go ahead, sorry.
Yeah, if I want to add from our perspective that yes, the drilling is the thing that we, for example, that's why we want to do in our SMARTrenew project. We are very interested in this experience and the project in Faroe Islands, because for the oldest parts of Iceland, we want to do something similar with grounded heat pumps. But the drilling cost in Iceland, even though we are experts in high risk, huge project drilling for power plants, it has been problematic to have these low-cost small drillers. They are just something that we don't have here in Iceland, and that what we need for the kind of the last 5%. So we are very interested in cooperating with Faroe Islands in getting this expertise that they are building up.
That's great. Listen, I'm going to, there's a couple of questions that have just come in here, and I think we'll probably, looking at the time's getting on for 12, we'll finish it up then. This is from Andy Frew again. Are you using big hot water tanks to store heat for a long time? Well, I know we're using a big hot water tank in Finland in one of our pilots in a district heating project there, but in general terms, I think this is to our panelists for maybe for the Icelandic panelists in particular, for the possibly, do you use big hot water tanks to store heat?
Yes.
That's it. And Husko, did you? Sorry, did I get an? I'm sorry, I'm looking.
I like just to mention that the storage can be underground also.
Yeah.
And they are building 2 big storages right now in Finland, one in Helsinki, one in Vantaa near Helsinki. The capacity is millions of liters, several tens of thousands of cubic meters, and they could provide heat for some hours during winter time. Normally the morning hours are when the need is the largest. So you can put the water underneath the ground also.
Okay, that's great. Thank you. And the last one, this is from an anonymous attendee, but we welcome them all. How can we increase geothermal power plant that already produces dry steam fluid? Is that the? I'm not sure. Does that ring a bell with anybody?
Yeah, I was talking about that. That's the best thing to have, dry steam. That means you have more heat and more pressure, which is what the turbines are operating on. So that's the best scenario you can get. That's what we're all aiming for in high temperature geothermal.
So that's yeah. So that's where that's the most potential. Okay. Listen, time has marched on. I just want to end this event. Just want to say a few thanks. Really want to thank all the speakers for taking their time, prepare presentations, and I'd like to thank everybody who attended. We had a great turnout. It was great to see people stuck with us to the end. And also, I'd like to thank Maria Gallagher, our SMARTrenew comms manager, for organising and all the promotion. And really, I just hope everybody has enjoyed it and got some information out of it. I'm going to share the last slide just with our contact details. And if you need or want to contact any of us, you can contact us through the SMARTrenew website. The details are there, but also our email addresses are throughout this presentation, and we're all you can find us online, no problem. If you have any more questions, we certainly welcome them. Any more questions come in that we haven't answered, we'll get back to you, and we will be sending a presentation, or we will be sending a recording of the presentation to everybody who participated and signed up. So we're going to sign out now, and thank you all very much for attending, and we hope you enjoyed it. Thank you and good morning.
Yeah, thank you.